In a previous video I calculated these false color images, and the purpose of these false color images was to calculate spectra from an imaging XPS dataset that were representative of the different chemistries across the analysis area. So in this video I'm going to take the spectra and make use of these spectra to fit the spectra pixels across the entire image, and in so doing calculate atomic concentration or compositional images that derive from the imaging XPS dataset. We construct the spectra by defining a false color mask based on the false color image, and this is performed using define image from F/C, that's false color image. So having selected a tile that contains the false color image, I press the button define image from false color and the mask is defined, at which point I can move to a corresponding imaging data set and overlay the images in the active tile, so I have all the data necessary to create the spectra, and then I can sum spectra using colors. The result of two colors will be two spectra, and so we end up with a new file that contains two spectra that are representative of different domains on the sample. Now if I go back and use this second false color image, I've now got a set of pixels that are defined that represent this wire. I can go back and create another pair of spectra using some spectra using colors. So I now have four spectra from which I can compute additional spectra if required using difference spectra. Let's have a look at what we've got. Let's normalize these. This is a Euclidean norm. Must have the same number of data channels in each spectrum to apply a Euclidean norm, and we certainly do have that, so that was applicable for these data, and I end up with four spectra, two very similar, two very different, representing gold, silver. The pixels may not have fully defined the zones that have different chemistry. For example, when we look at the gold, we might expect there to be an element of the glass that surrounds the gold also included in these data, and to some extent we can see there are structures that might be consistent with some of the glass. So let's use the glass that was calculated that was not gold, and we can see here and here examples of where the silicon peaks ought to be, and you can see in the background an element of that, but we can also see here a bit of the silver, and that's because in the second abstract factor all the glass and the silver are included in the green spectrum. So if I wish to work on removing the glass from the gold, it's probably better to use a spectrum that includes not silver. And although there's a little bit of silver here, I can see that predominantly the glass spectrum here has some gold and very little silver. Well, I could actually try and remove some of the silver from the glass that has a little bit of evidence of silver, and this could be the first example of a different spectrum. So I've taken these two, I've overlaid these in the active tile in the order that I wish to perform the subtraction. So I want to produce a glass spectrum that has no silver, so I've selected the glass first and the silver second, then performed a difference calculation which has the result of producing a set of spectra that progressively remove from the one spectrum a proportion of the other. I've now removed the silver. If you look here, whereas initially there's a little evidence of silver, by subtracting off a little bit of the silver spectrum, I've ended up with a background instead of signal that might be associated with silver. So that's the first problem, is to produce a spectrum that is glass and no silver. So let's copy that into the construction file. So now I can look at the gold and say I want to remove from the gold a little bit of the silver also. Perhaps not. I was anticipating this to be silver, but this does not appear to be silver. In fact, it's probably a gold signal. So that makes me feel quite comfortable that I've got within this blue spectrum gold and a bit of glass. So let's use the gold and the glass to remove these small peaks here, again using different spectra. And as I go down this list, and I'm looking here at the silicon, so I now believe I've got something that looks like I've removed the silicon from the gold spectrum. I'll take a copy of that, and I can then copy that into my working file. So I've now got two spectra that I've calculated using different spectra. One is now pure gold, the other is mostly the glass, and the third piece of this jigsaw is the silver. So I've now got three component spectra that I can organize and make use of to fit the spectral pixels of the entire data set of images. I can apply these component spectra to spectral pixels if I go back to the imaging data set and create a set of spectra at pixels. So these are spectra at pixels organized as a set of corresponding variables in VAMAS blocks. So to use the analysis that has been performed here based on different spectra and apply to these data, I need to copy the component spectra into the active tile that contains these spectra at pixels in this particular format. And then if I select the column of spectra at pixels with the three component spectra displayed in the active tile, then I can use the linear analysis button that will then cause the fitting of these three spectra to each and every one of the spectra at pixels that are within these VAMAS blocks. So on completion, we again have the spectra at pixels in the same format as the original data file, but now we have the linear least squares fit to these data that now gives us the ability to characterize the image of the entire analysis area in terms of these three component spectra.